us work out the next problem. That's problem number 8. Almost similar to one of the models what we have taken up earlier. We have calculated current in one of the problems. Now we people are calculating the induced EMF, almost in the same model. A coil has 1000 turns and 500 centimeter square as its area. The plane of the coil is placed at right angles to a magnetic induction field of 2 into 10 power minus 5 Weber per meter square, which of course is Tesla once again. The coil is rotated through 180 degrees in 0.2 seconds. The average EMF induced in the coil is how much? So almost similar model, but earlier we have calculated in the same model what is the induced current like. Now we people are calculating induced EMF like. This model, since it is a very, very important model, you should not consider this one as a repetition. It's a different calculation we are having in this problem. Once again I repeat, when the coil is rotated by 180 degrees, the moment we consider that, already I have explained you earlier also, the change in magnetic flux becomes doubled. So you can directly write this way, E being minus d phi by dt now can be written as NBA by T. And what is this N over here? Number of turns, B the magnetic induction, A is the area of the coil, fine. But when it is reversed totally or rotated by 180 degrees, this phi to be taken twice BA, therefore this becomes 2 times. And automatically that negative sign becomes positive, because the final flux if I take minus phi, initial flux if I take plus phi, final minus initial, that becomes minus 2 phi, that minus of minus becomes plus, so automatically that becomes positive over here, twice NBA by T. What are the values he has provided? You see there, N is 1000. B value is mentioned 2 into 10 to the power minus 5. Area of the coil totally is given 500 centimeter square again, that you can write 10 power minus 4 meter square over how much time that has been given in reversing this coil, that's 0.2. So better take 2 into 10 power minus 1. So 3 zeros over here, 2 zeros over here, 10 power minus 5, totally you cut it off, 2 goes off here. Now 2 into 5, it is a 10, that cancels here minus 3 times. So you people are directly getting here, right, 10 to the power minus 3. What? Is just giving you 10 to the power minus 3 volt. Right, N is given 1000, B is given 2 into 10 power minus 5, A is given 500 into 10 power minus 4. By the value of T that has been mentioned, 0.2, 2 into 10 power minus 1, I have written like that, right. This is 10 power minus 3, this 10 comes up, so 10 into 10 power minus 3. So what we can write now? 10 millivolt, that is the concept. So out of the 4 options given, first option is 5 millivolt, second is 10 millivolt, third one is 15 millivolt, and fourth one is 20 millivolt. Out of them, the second one is the right option for this particular problem. So answer for this one is simply B. So already we have discussed one model like this earlier, but there we have calculated current. Now here we are calculating the value of EMF. But once again I repeat, the moment the coil is reversed in its direction totally or rotated by an angle 180 degrees, then phi becomes doubled. That's the only area one should concentrate much on. So that is problem number 8. The answer for that one is B, which is 10 millivolt as such. So let us check the next problem here, that's problem number 9. A current of 2 ampere is increasing at the rate of 4 ampere per second through a coil of inductance 2 Henry. The energy stored in the inductor per unit time is how much? It's a wonderful concept. If you are not reading the problem carefully, you may simply calculate the energy there. He is not asking you energy. Energy is stored in the inductor per unit time he is asking. That is nothing other than rate of energy stored. That is, rate of energy stored in this particular case is nothing other than power he is asking you. It's work by time or energy by time. Whatever you talk about, that is to be called as power there. So that is the point one has to understand. So what are the values he has given? You see once again as far as the options are concerned. First option, it's given 2 watt. Second option 1 watt. Third option 16 watt. And fourth option 4 watt. These are the 4 answers mentioned. Correct answer obviously is C, that is 16 watt, which is the total power. So if you look at this one, generally energy stored in an inductance coil is going to be half Li square. That's the formula. Energy stored is half Li square. But when I want power here, that now can be taken rate of energy stored. This of course we can rewrite the same this way, half L into 2I di by dt. So if you look at this one, 2 getting cancelled. L is inductance. What is the value mentioned over there? You look at, it's 2 Henry given as L. What amount of current that is flowing, he said? The current that is flowing is given again as 2 ampere. In addition to that, what is the rate of flow of current across the system? At a rate of 4 ampere per second, that's what he is talking about. So di by dt now becomes 4 here. So automatically this now becomes 16. Since it is the power, we can write the unit as watt. So what is the concept here? You try to understand. He is asking you the energy stored in the inductor per unit time. Per unit time, that means the rate of the energy stored. The rate of the energy stored is nothing other than half Li square. You take the energy like du by dt, which now becomes half of L into 2I into di by dt. So in other words, simply speaking, Li di by dt, that is the final formula. So it now becomes 16 watt, which of course is tallied with the third option given in the problem, or in the just 4 options like. So answer for this question is now becoming C. That is problem number 9 what people are having. So energy stored in an inductance, half Li square, that is the formula. It's more or less like half mv square only, but here it is half Li square. Similar formula of course we will be coming across in different other chapters also. Energy stored in a spring, like when we consider a compressed spring, it is half kx square we write. Like that here half Li square we write. General kinetic energy formula half mv square we all know. Rotational kinetic energy we know half I omega square like. So all are just similar formulae what we people are going to have. So this is problem number 9, and the correct answer for that one is 16 watt, which is the correct option as C over here. A very interesting description has been made in the next problem. That problem number 10 I am talking about. A physicist works in a laboratory where the magnetic field is 2 Tesla. She wears a necklace enclosing an area 100 centimeter square of the field and having a resistance of 0.1 ohm. Because of power failure, the field decays to 1 Tesla in 1 millisecond. So what is that? You can understand here. 2 Tesla is the original or initial magnetic induction of the field. Power failure, due to that 2 Tesla has come down to 1 Tesla by decaying. So what happens? When it is decaying there is a possibility of rate of change of magnetic flux produced in the system. Constant magnetic flux, suppose if you are having, you will never used to find any induced EMF. Magnetic flux variation with respect to time is necessary for us to get induced EMF in general. Now, okay, what is he asking for? He said because of power failure, the field decays to 1 Tesla in 1 millisecond. The electric charge circulated in the necklace, assuming that the magnetic field is perpendicular to the area covered by the necklace, is how much? How much charge that is being circulated in the necklace? That's what he is asking you. So what we can understand here? Out of 4 options, he gave the first option as 0.01 coulomb. Second option as 0.001 coulomb. Third option 0.1 coulomb, and fourth option 1 coulomb. The correct answer for this one is C, which is 0.1 coulomb as such. So according to the given problem, let us once again work out what is going to be the charge that is in the necklace. As usual, induced EMF is minus d phi by dt. That is a known equation. In fact, I should say the entire electromagnetic induction chapter. Whatever be the model of the problem, let them give. That is a different issue. But there is only one formula overall in this chapter. That is this one. That only we used to write in different ways, in different forms. So if you look at d phi by dt, this now can be written as IR like. As well as it is, I have told you earlier also. According to Ohm's law, is IR. If I take this I, dq by dt like, we can write that one into R. In fact, dt getting cancelled, q of course we just have to take. Therefrom, I can write the charge q is NBA, that is d phi, linked with the coil, in this particular case the necklace. NBA divided by the value of R. So you can directly understand this one, how to take this value of B now. N no doubt is 1, only one necklace it has got. And what else the B value? It's 2 minus 1 we should consider. Because originally it was having 2 Tesla, the magnetic field. Now when the power has been failed, due to the power failure, it has come down to 1 Tesla. So what we should understand, the area here of that necklace has been given very clearly as 100 centimeters square. So write 100 into 10 power minus 4 meter square as such. What is the resistance of that he has given? It's 0.1 ohm. That's what he has given. So you can write directly 10 power minus 1. Now okay, this anyhow becomes 1. So this cancels here minus 3 times. So 100 into 10 power minus 3, which now becomes 0.1 coulomb. 0.1 coulomb charge is a minute value. Suppose if the charge is very, very high by any chance, no one can wear a necklace. Necklace having so much of charge means who will bear that? Not possible at all. Therefore, the point here to be noted is, after calculating the value also, you should come to a conclusion, yes, whether this amount of charge that's possible over there or not, by any chance, by mistake. I have got something like 10 power 4 coulombs or 10 power 5 coulomb like. Then when one has to think of, will a necklace be having that much amount of charge like? No, no chance. So once again, if we go back by one step, you will come to know where you have gone wrong. So what is the correct answer here? 0.1 coulomb. That is the amount of charge what we people are having across that necklace like. So while taking up the difference over here, automatically that negative sign automatically becomes positive there. So no need once again for me to write that value. So it is 0.1 coulomb, which of course is exactly the same option given in the problem as C. Look at that one, C, third option is given 0.1 coulomb only. So correct answer for this particular question is C. Only thing is, the question is looking lengthy because he has described how she is wearing the necklace, what kind of a necklace she is wearing there, how the magnetic field is varying over there in the system due to power failure and other things like. So problem is looking lengthy, but the common formula, which of course we people used to take up in this chapter, as I have already told you, that is this only. That only we write in different versions for answering different questions over there. So the correct answer for problem number 10 is C, which is 0.1 coulomb as such. Probably most of you people might have recognized this problem, what we people are discussing right now. That's problem number 11. To my knowledge, this particular problem has been asked almost in every entrance examination of every state, and this was one of the problems in JEE. That means you can understand the standard of this problem. A small square loop of wire of side small l is placed inside a large square loop of side capital L. He has given in brackets capital L is greater than small l. The value is so high, that's the point. And what else he is talking? Carrying a current I. If the loops are coplanar and their centers coincide, the mutual induction of the system is directly proportional to how much. So that is the concept what he is talking about. And 4 options are given. First option, capital L by small l. Second option, small l by capital L. Third option, capital L square by small l. And fourth option, small l square by capital L. In fact, the correct option is the fourth one. Small l square divided by capital L, that is the concept. In fact, we all know whenever self-induction or mutual induction that has been taken up, we can directly write the concept this way. That is, the value of phi is proportional to I. N phi is equal to Mi. This is the formula generally we write. And what is this concept over here? In fact, phi is proportional to I. The total flux linked with the coil having n number of turns, we write that one as n phi. That n phi is equal to a constant into I. That constant here in this particular case is mutual induction, coefficient of mutual induction. So this is what actually he is talking. But of course we know pretty well what is phi. It's nothing other than B times A. So N B A is Mi. Now if you just take this M over here, that now becomes NBA by I. That is the concept officially. So what is it he is describing here? You see, there is a very big square loop like, and there is a very small square loop placed inside. And he said they have common center. Their centers are coincided. Now in addition to that one, he is talking about its length as L and its length as L. And of course he said is placed inside a large square loop of side capital L carrying current I. That is the point. So first and foremost, when you talk about that it is carrying current like this as I, what will be the magnetic induction at the center of the square coil? According to right hand rule, you all can directly understand what is the direction of magnetic field produced due to this passage of current. If I take, this is the direction of current here, this is the direction of current here, this one the direction over here, this is the direction of current here, for example. Then if I stretch my right hand, the thumb should show the direction of current here. The magnetic field at this point is outside the board. Same is the case with it. Same is the case with it. In fact, same will be the case with this one also. So what we should understand? We should take it for granted the magnetic field due to one side, if I call it as B, the effective magnetic field at the center now becomes 4B. Because this is B, due to this one it is B, due to this one it is B, due to this one also it is B. You should understand all the four have the same direction. That too the direction is outside the plane of the board, perpendicular to the plane. Thereby we have to add them vectorially. So B plus B plus B plus B now becomes 4B. So what will now be this effective value of B now? It is 4 times B, I said. Fine. But how do we get this value of B? Everybody must have got the idea of magnetic induction due to a finite long current carrying conductor at a point. For example, if I just connect this one over here, connect this one over here. This will now be the perpendicular distance, which of course is going to be L by 2. And this angle will now be 45 degrees, this angle will now be 45 degrees. Recollect what is the formula there? Mu naught by 4 pi. I by R. R is this. So I by L by 2 into sin phi 1 plus sin phi 2. If I take this angle as phi 1, this angle as phi 2, you can easily understand from this figure phi 1 and phi 2 both are equal to 45 degrees. Then what is sin 45? 1 by root 2. Again 1 by root 2. 1 by root 2 plus 1 by root 2, which is 2 by root 2. That can now be written as simply root 2. So this now becomes root 2. So what is it you are getting out of this one now? This becomes 2 going up, 2 for the 8 root 2 into mu naught I by 4 pi L, that is B. And of course N is not mentioned here, that means only one loop. One should consider N as one only. He has not mentioned how many number of turns we have in that square loop like. So N should be 1. B now should be this effective value. And what is area? Area of this smaller loop into which the induction is taking place. So what is that smaller loop's size? It is small L, the size of it, the length of it. Length of each side like I am talking, and it is a square loop. Then what can I write? Therefore M is equal to B effective, which now is 8 root 2 into mu naught I by 4 pi into L into area, that now becomes L square. It is a small square loop. Its area can be taken L square, we know it very well. Now his question is, M is proportional to what? Better understand this one. 8 root 2 is a constant. Mu naught constant, 4 pi constant. Constant current is just passing through that one also he has given you. Now what else? It is proportional to L square by L. So which L square by which L is the criteria? Because he has mentioned two options over there. Option number 3, that is capital L square by small l. Option number 4, small l square by capital L. Now you should understand this way. It is due to the current passing through the greater loop. The induction is taking place in the smaller one. Therefore, it should be taken L square by L. Which L square? Small l square by capital L now must be your answer. So, which is in coincidence with the fourth option which has been given in that order. So, what is the correct answer for this? It is capital M, which is coefficient of mutual induction, that is directly proportional to small l square by capital L, where small l is the side length of the small square, which is placed inside another square of side length capital L. So this is the concept one should understand. So it's proportional to he is asking, not asking you the total value and other things like. So you can directly go ahead with this methodology. So correct answer for this one is D. Most probably, most of you people might have already observed the correct answer out of the lot. Such known questions, suppose very well noted questions, generally students will never do. They take it for granted. What is the correct answer there? The correct answer is L square by L. Which L square by which L is the criteria? That's all. Other than that, problem is easier. But what is the formula we have applied here? That you need to recollect once again. This is an application of Biot-Savart's law. Based on that, when a straight conductor of a finite length is carrying some amount of current, what would be the magnetic induction at a point which is at a certain distance from the conductor? Followed. So that is the concept what we have applied, and this is the answer for this. Let us check one more number, one more problem, which is a very commonly asked model like. That's problem number 12 I am talking about. Let me read out. Two coils have self-inductance L1 as 4 millihenry and L2 as 1 millihenry respectively. He is just giving you the coefficients of self-induction. 4 millihenry the first one, 1 millihenry the second one. These are the values he has provided. Fine. Let us continue. The currents in the coils are increased at the same rate. At the same rate, currents are increasing. The moment it is given that way, you should immediately get your mind that di by dt is constant in both of them. Rate of change of current. That itself is given in other wording, like currents are increasing at the same rate. That's the point. Now what next? At a certain instant of time, both the coils are given the same power. That is another point. So you can immediately get your mind the power 1 of the first coil and the power 2 in the second coil are equal. Now what is he asking for? Check that. If I1 and I2 are the currents in the two coils, at that instant of time respectively, then I1 by I2 is how much? He has given you 4 options once again. First option is 1 by 8. That's 1:8 ratio I1 is to I2. Second option is given 1 over 4. It's 1:4 ratio he is talking about. Third option is given 1 by 2. The ratio is 1:2 like he is just giving us. And fourth option he gave it as 1. That means I1 and I2 are equal according to this fourth option. Whichever one that's correct over here, we have to pick up now. The correct option for this problem is the second one. That's I1 by I2 is now going to be 1 over 4. That is the correct option for us. What for you can think of? This is in fact the clue for you. As such, we know energy stored in any coil, that is half Li square. Already we have discussed this earlier. Now power becomes rate of doing work or rate of the energy. It's energy over time. That's what is called power. Now in this particular case, you can write half L as it is 2I di by dt. That is the way we people used to write this equation. I have already told you. 2 getting cancelled, you now are left with power is equal to Li di by dt. Check carefully the 3 terms L, the coefficient of self-induction of the coil given. For the first coil it's given 4, for the second coil it's given 1 millihenry. The second one is current. In fact, this ratio he is asking you to calculate. And di by dt is rate of increase of current. He said very clearly the currents in both the coils are increased at the same rate. So already I have written di by dt according to the description, it is constant. Then when this is constant, power should be proportional to L into I. and he gave powers are equal. That is the rule. That is a condition what has been mentioned. But powers are equal. Then what I can write now? This gives you L1 I1 must be equal to L2 I2. Power values are equal in both the cases, in both the coils. That's what has been mentioned there. So what can we write now? L1 I1 is equal to L2 I2. Now see which ratio he wants. Is it I1 by I2 or I2 by I1? He is asking you I1 by I2 is how much? So straight away we can write from this one that I1 by I2 now becomes L2 by L1. Already I have mentioned the values given in the problem for L1 and L2. L2 is given 1 and L1 is given 4. So what must be the correct ratio there? 1 over 4 must be I1 by I2, or I1 is to I2 is 1 is to 4 like. So this particular answer what we have got now is exactly the same given in the second option of the question. So what is the correct answer for that? Answer now becomes B, that is 1 over 4 or 1 by 4 is I1 by I2. That is question number 12 what has been mentioned here. So only thing you should understand in this particular question, while reading itself, you will not find time to read several times the same problem. While reading for the first time itself, what are the values mentioned, you should be thorough with. Di by dt is given constant, you can identify from the second sentence. And powers are equal, that is ultimate condition based on which he is asking us to calculate I1 by I2 in this case. So this is actually the answer for that. 1 by 4 is the right option, which of course is the second option which is correct over here for problem number 12 what we have. The next problem, that is problem number 13, once again is based on induced EMF. Two parallel rails of a railway track insulated from each other and with the ground are connected to a millivoltmeter. He has very clearly mentioned both the rails are insulated from each other and with the earth. That means what? Whatever the charge they are getting is not conveyed to the earth, and whatever the charge or EMF whatever you are finding over there across those two will never be transferred from one to the other, like they are insulated ones. That wording is very important for us. The distance between the rails is a meter. A train is traveling with a velocity of 72 km per hour along the track. If vertical component of Earth's magnetic field or magnetic induction is 2 into 10 power minus 5 Tesla, the reading of millivoltmeter is how much? Voltmeter in fact is just connected over there to measure EMF. Millivoltmeter, after all, what happens in that case is the values what you are observing there, they will be in millivolt, that's all. But voltmeter ultimately is going to measure EMF only. There is nothing in that. This again is based on motional EMF. What is the formula for this motional EMF? Already we have discussed. BLV cos theta or BLV sin theta. Whether you take in terms of sin theta or cos theta, depending on the phase of the coil or the perpendicular drawn, you are getting the maximum value as this much. What is this B now to be called? Simply vertical component of magnetic field of Earth. That value is already provided to us as 2 into 10 power minus 5 Tesla. What next? Length. It's given a meter. He gave very, very clearly that the distance between the rails is 1 meter. That means across these two rails only. of distance of separation 1 meter, we just want to calculate the induced EMF across the terminals of those two. So you can understand with what velocity that train is now running on the track. He gave 72 km per hour. In fact, every one of us we know it's 20 meter per second. So you can directly cut this one over here minus 4 times. So 4 into 10 power minus 4 volt like. But he is talking about reading of the millivoltmeter. As I have already briefed you in the beginning, millivoltmeter after all gives the values in millivolts, that's all. So what is its reading, the question? So you directly can write 0.4 into 10 power minus 3 volt, which can be rewritten 0.4 millivolt like. So options, if you look at 144 millivolt is the first option. 0.72 millivolt the second option. 0.4 millivolt the third option. 0.2 millivolt the fourth option. So which is the correct option over here? 0.4 millivolt, of which the answer is C, given in the 4 options of this particular problem. So 0.4 millivolt, which is the third option, that's going to be true for this problem number 13, what we are having in this order. Let us work out the next number. That's problem 14. A coil of 30 turns of wire, each of 10 centimeter square area, is placed with its plane perpendicular to a magnetic field of 0.1 Tesla. When the coil is suddenly withdrawn from the field, a galvanometer connected in series with the coil indicated that a 10 microcoulomb charge passes around the circuit. So one can directly understand, when you are withdrawing the coil from the field, then automatically magnetic flux varies with respect to time. That means rate of change of magnetic flux is observed. That in turn produces induced EMF. That in turn makes some current pass across the system. Current is nothing other than rate of flow of charge. So according to this problem, when the coil has been withdrawn from the field, a charge of 10 microcoulomb that is now passing around the circuit. That's what has been mentioned. Then what is the question? The combined resistance of the coil and the galvanometer is how much? Combined resistance. Once again the same concept, of course. But let us first of all finalize what are the options given. The very first option is 3 ohm. The second option there is 30 ohm. Option 3 is 300 ohm. And option 4 is 3000 ohm. So the correct answer over here is simply 300 ohm. That is the third option which is correct. Let us check once again. We in fact know, once again, EMF is minus d phi by dt. No change in this formula anymore till we complete this chapter. E, of course, we can write it as IR. I said I can be rewritten as dq by dt into R, I said. Then you have a direct formula. Q is equal to NBA by R. Already we have taken this formula in one other problem. Now here he is asking you the question in a different mode. What is the value of resistance of the combination of the coil and the galvanometer? Combined resistance he is asking. And you know pretty well the coil is connected in series to the galvanometer. So the combined resistance is nothing other than the sum of their individual resistances. So you can say R now becomes NBA by Q. According to this formula, R is equal to NBA by Q. Okay, let us once again check the values provided in the problem and let us substitute them in this formula. N is given 30 turns. Fine. The value of B that has been mentioned over here as 0.1 Tesla. Area of the coil given 10 centimeter square, not meter square, 10 centimeter square. So 10 times 10 power minus 4 meter square. And how much charge that has been observed in the galvanometer, you check that. It's now 10 microcoulomb. So 10 into 10 power minus 6. Now in fact this point and this 0 you can cut that one off. This 0 you can cancel that one over here. This cancels 10 power minus 2 times. If 10 power minus 2 comes up, automatically that becomes 300 ohm. As I have already mentioned the 4 options, third option is given 300 ohm over here. Therefore, the correct answer for this particular problem is C. That is what you have to understand. Only thing in this case is, once again, Q is NBA by R. Out of that, resistance of the combined system he is asking. Combined means one should understand that galvanometer always is connected in series to the coil. So when galvanometer is connected that way, the coil resistance plus a galvanometer resistance, that now becomes the entire resistance in the circuit or combined resistance of both of them in the circuit. That's what he is asking, and its value is now 300 ohm. That is option 3, that is C here for the problem number 14 what we have. Let us switch over to the next number, that's problem number 15, which has been one of the EEE questions. A magnetic field in a certain region is given by B bar is equal to 40I minus 15K into 10 to the power minus 4 Tesla. The magnetic flux passes through a loop of area 5 centimeter square, which is placed flat on XY plane, is how much? 4 options. I read out the first. 750 nano Weber. Second option, minus 750 nano Weber. Third option, 360 nano Weber. And fourth option, minus 360 nano Weber. Correct answer for this one is B. That's the second one. Minus 750 nano Weber. That is the correct answer for the magnetic flux that is passing through the coil. What are the values given? Let me write here. He gave the magnetic field in the form of a vector. The vectorial form he gave. 40I minus 15K into 10 power minus 4. I directly write this way. 40 into 10 power minus 4I, that is x coordinate of that, minus 15 into 10 to the power minus 4K. This is its z coordinate. Totally, he gave the units as Tesla, Weber per meter square. What next he said? There is a coil. That coil of area, how much he said? 5 centimeter square he has given. That now can be rewritten 5 into 10 power minus 4 meter square. Till that extent, okay. Now observe the last sentence carefully. the magnetic flux passes through a loop of area 5 into, that is 5 into 10 power minus 4 meter square or 5 centimeter square, which is placed flat on xy plane. Observe, for example, this is x and this one is y. If I place that loop on xy plane, flat on it, then you can understand well magnetic flux that passes through the coil along z-axis, perpendicular to x and y planes. XY plane, what is that plane which is perpendicular to x and y? That will be z. So what we should understand here in this case is phi we just want, which now is B dot A. That is the formula you should understand. Now which B to be taken? B along z-axis to be taken. Why along z-axis? The loop or that coil, whatever he is talking about, the loop or coil, whatever it is, when it is flat on xy plane, the lines of force will pass through that coil perpendicular to that xy plane. Perpendicular to xy plane is going to be z-axis. So the value of B, the coordinate of B along z-axis is to be taken here. So what will be that value? Minus 15 into 10 power minus 4 into, what is the other one? 5 into 10 power minus 4. Actually B dot A, it is BA cos theta, and cos theta is 1, therefore it is BA. B, which axis value we have to take? BZ into A. That's the only point you should understand, nothing else. So what I can write here? 5 times 15, it's 75 into 10 power minus 8 with a negative sign, Weber I can write. But he has not given directly the answers in Weber, nano Weber he gave. So you can write this one minus 750 nano Weber. And you can certainly understand where from we are getting this negative sign. Negative sign is in the coordinate along the axis of B. So that value with that same sign we have to consider, otherwise we go wrong. First option you look at, plus 750 nanoweber, but that is not the right option. Correct option is the second one, minus 750 nanoweber here. So if you look at B dot A, which of course is BA cos theta, that of course cos theta when it is 1, that time you will be getting phi as maximum value. That maximum value is B into A. Which coordinate of B to be taken? That is important here. Coordinate of B along that axis perpendicular to the plane of the loop we have to consider. Since the loop is placed on xy plane, then automatically the perpendicular direction of that one will be along z-axis. So one should consider the coordinate along z-axis in place of B into A. A is area. He has mentioned directly we will be getting minus 750 nanoweber, of which this is tallying with the second option given out of the 4. So the correct answer for this problem number 15 is minus 750 nanoweber, which is the second option over here in this problem that's given. So this is problem number 15 what we have.